Swayam Prabha. Digital India. Educated India.
Welcome back to this course on cyber physical systems. So in the previous lecture we have been talking about CAN bus and how such CAN buses work, right? So let's switch over to the slides from where we left. Yeah, so we are talking about typically the properties of a CAN bus, right? And we said that a CAN bus is at the physical level, although it's not enforced, but the way the CAN bus is implemented is it's a twisted pair cable where there are two signal buses, two signal lines, the CAN high and the CAN low line. Okay. So what happens is they maintain. The overall this bus, this twisted pair has two states. It's either in dominant state or it's in the recessive state. So when it is in recessive state, that means this CAN high and CAN low, they are both biased positively with a voltage of 2.5, hence there is no voltage difference between them. So that is the recessive state. And when we say that the bus is in a dominant state, that means CAN high will assume a voltage value which is 1 volt higher, so that is 3.5 volt, and CAN low will assume a voltage that is 1 volt lower, that is like 1.5 volt, and this will create a 2 volt difference. So this is something like 3.5 here, and let's say that when this guy who is in the CAN low, so this is CAN high, this is CAN low, here it will come down by 1 volt to 1.5, okay, and this will create this kind of a 2 volt difference here. Okay, so this is the dominant state. Now what is the corresponding bit encoding? So when you say that the bus is in a dominant state, we interpret this as a logic 0, and when we say that the bus is in a recessive state, we interpret that as a logic 1. Okay, so when actually there is no voltage difference between the two lines in the bus, so that's a logic 1. That's a logic 1. It's recessive, and when there is a voltage difference of 2 volt, then we have this as a logic 0, and that is the dominant state. Dominant state because you really have a signal difference here. So we'll just write it in a better way. Yeah. Now something very important, that how the CAN voltage signal is going to represent a bit pattern. So the CAN encoding type is called NRZ, or non-return to 0. So as we know that in a digital signal you have two possible ways of representing bit patterns. So let's say is time, and for each bit you have an allotted time period for the transmission. So let's say you are writing a signal which is high from here up to this. So you can say that I have a 1, then a 1, then a 1, then a 1, like that. Okay, so this is a non-return to 0 encoding, because whenever it is high, it's a 1. That's how am I interpreting it, right? The alternative would have been this goes high, then it comes down. Then for the next one, again it will go high and come down. Again it will go high and come down. It is always going high at the edge of the clock. Okay. Again it is going high here and then coming down like that. So you can see that we have a positive edge at the clock when the signal is going 1. So which is actually good for synchronization. So that is a return to 0 type encoding, and the previous one that I showed is a non-return to 0 type encoding, and can actually follows the non-return to 0 type encoding. But the problem with that kind of encoding is that it is easy to implement, it is cheap, but the bus, I mean you may lose synchronization, the nodes may lose synchronization with the bus for the simple reason that the signal is continuously 1 or the signal is continuously 0, and there is no switching activity happening. The good thing about the switching activity is that the switching happens at the clock edge, so that gives me some signal to synchronize with. As a node, I get a signal to synchronize with the bus, that well, this is where the bus's one transmission cycle is beginning, something like that. So what is the solution? The solution that so that it is not continuously enforced, that I can be allowed that I am always a 1. The rule says that well, if you have 5 consecutive bits which are either dominant or recessive, you must have 1 bit in between of the opposite polarity. So this is known as bit stuffing rule. So that means that bit doesn't have any related information. It's just a bit stuffing rule of CAN, which is breaking this pattern of continuous dominant or continuous recessive state, and 1 bit in between of opposite polarity is also helping you to get the system synchronized back. Because and fundamentally, why is the synchronization system problem comes because different nodes are having their different local clocks, and of course, like we know that clocks may slowly drift, right? So that leads to this whole problem of synchronization. But coming back here, let's just restrict ourselves to the understanding that for long periods, if there is no clockage that is happening on the bus, there is no switching activity, the individual nodes may lose their synchronization with the bus. That means they will be unaware of the exact times when one cycle of transmission starts or ends in the bus. That is why to break out of this issue, this rule exists. Okay. Now, of course, this stuffed bit needs to be understood. That means the protocol will also do suitable destuffing of this bit from the original message at the reception side. Now let's open up a CAN packet and see what are its contents. So this is typically how a CAN packet would look like. So initially you have a start of frame bit, so it's 1 bit which is always dominant, and it is telling you that one CAN frame has started. Then you have an identifier. So identifier is an 11-bit field, and that is kind of indicating the priority of the message. So it will have a bit pattern, and that would also mean that if the bit pattern is of having a lower value in binary, then the priority of this message is higher. Okay. Now after that there is 1 bit called remote transmission request, requesting other nodes, and then we have 2 bit in reserve for future usage, and then we have the data length code, the DLC. Now the DLC has a usage. If you see after the DLC you have a field called the data field. Now this is the actual packet, the payload that you are sending inside this CAN packet. Okay. So this data field it's written 0 to 8 bytes. That means that we are not fixing a fixed number of bits in every packet for data transmission. We are saying that well, the data may be large, the data may be small. It depends on the application. So let it vary from 0 to 8 bits. This is good from an embedded resource constraint system point of view, because if there is less amount of data to process or send, why book more number of bits in this field, right? And the data length code is actually telling me it's a 4-bit, its length is fixed, right? And it is telling me that well, what is the size of the actual data field. So this is a smart decision to have some bits for DLC, and having this some bits for DLC is actually helping you to keep the original data field kind of variable in its length. So after this you have the CRC, so cyclic redundancy check. So that's a standard. There are standard CRC algorithms to kind of store the integrity of a message, that well, if you have a valid message, let's say your message is x, using a CRC polynomial you can compute some px, and these two things together you can send. The reason being, suppose somebody is perturbing this x, then at the reception side, somebody who will be knowing the CRC polynomial, he can actually compute this px for this modified x. Let's say it has become some x prime, and now what will happen is whatever p prime he computes, they will not match, right? From there it will be known that well, whatever was sent has lost its integrity. Okay, so this kind of checks, that's why they are standard and they are implemented in CAN buses also, but it is known that nowadays that this kind of security measures are quite easy to break also. Now the next thing is a CRC delimiter. So this is one delimiter field. After this delimiter field, there is an acknowledgement bit. Now the transmitter sends recessive and the receiver will assert in dominant. So this has a standard that whenever the transmitter is sending, in the acknowledgement field he will send a recessive signal. That means a voltage difference. That means a voltage difference of 0 would be set, right? Or a logic 1 would be set, and the receiver will assert a logic 0. That means a voltage difference of 2. That is the dominant bit. So when the transmitter sees that well, I have sent this in a recessive mode, but it has become dominant, then he would know that well, the receiver has indeed received it and acknowledged it. So in this way, the transmitter knows that the frame has been received by at least one receiver. If whatever he is sending as an acknowledgement bit in this field is immediately getting flipped in the CAN line, because as we know that in the CAN line everybody can see and read the message, and whenever somebody is sending, he can also simultaneously see that whether that message value is getting changed inside that same transmission cycle or not. Now after this there is a delimiter, which is the acknowledgement delimiter, and this is always recessive. And after this there would again be a end of frame of 7 bits, and that's also recessive. Okay. Now one more question: what is the use of these delimiters? These delimiters tell you that there are certain fixed positions in this bit pattern which would be recessive or which would be something different. So any change there would also tell you that well, this packet has somehow been spoiled by some attacker or by some environmental noise or something. You know that the end of frame has to be 7 bits recessive. If that is not so, then you know that the packet has an issue. You know that there is a delimiter CRC at this position and that is going to be a recessive bit. If it is not so, you know that there is an issue, right? So and so forth. So the CAN clock is usually synchronized using this start of frame bit. Now these nodes rapidly lose synchronization when the CAN bus is idle. Now the idle bus has no transitions, and the idea of bit stuffing applies only to when the real messages are sent. So when there is no message sent, then the bit stuffing rule doesn't even apply, right? So this is an issue, right? So the nodes will also resynchronize on every recessive to dominant edge. So if you see, the start of frame is always dominant, and dominant means there is a positive voltage difference that would get created, right? So that is kind of a signal which is used for the nodes to get together synchronized and make that as a start of a transmission cycle in the system. Now how do I address nodes? Because in computer science or any embedded real-time system design, whenever you have multiple things to connect, you would like to number them as 1, 2, 3, etc. like that, right? So in this case, you don't have addresses for nodes, rather you have identifier fields for messages. What does a message represent? So the way we interpret CAN messages is a bit different. So it works like this, that so suppose I am sending a message. So the thing I am trying to say is that well, I am an ECU which is sending an oxygen sensor reading. Okay, so it's not like that I am saying that well, this is a message and I am sending it to that node. Okay, so this is all multicast communication. Everybody can see what everybody is transmitting. So whenever I transmit something, I don't give this an address that you send this value, I am sending this value to node X. Instead, I am just advertising that, well, this value I am sending is of this type, and that type is kind of understood from that 11-bit identifier field, okay, which in an extended CAN system, it can be a larger. Suppose, and why do I need a larger identifier? Suppose I have so many different types of messages, right, that the identifier field needs to be enhanced, then there is also an option of having this kind of a 29-bit identifier. So, okay. So, what is important is what is the message type, and the message type is defined by the identifier. It's not important that who is sending and to whom it is going, things like that, okay. From the message type, everybody knows that, well, this message is of this type, and accordingly he or she will get it read. So, there are multiple different types of frames in CAN. So, you have the data frame, which is the standard CAN message broadcasting data from the transmitter to other nodes on the bus, okay. And then you have a remote frame, which is broadcast by a transmitter to request data from a specific node. So, data frame is just the standard CAN message that we discussed. Remote frame means, suppose some node request data from a specific node, so that would be a remote frame. Error frame is a special type of frame which is generated by a node when a bus error is detected, and overload frames are kind of frames which are used so that whenever the system detects that there is too many number of data packets on the bus and they are not getting used, and there is a lot of the data has no real consumer, one would like to insert some delay between future transmissions, and that is done by transmitting this kind of overload frames. Now we come to the issue we pointed out earlier. Like we said that CAN has a very nice arbitration scheme, right? So this arbitration scheme will determine that which of the nodes attempting to transmit together will actually control the bus. And like we said earlier, that this is not so in CSMA CD, carrier sense multiple access or collision detect type systems, because in such systems anyone can transmit when the medium is idle, and then if there is a collision, that would be detected, and then the current packet the transmissions will stop, and then each of the nodes would back off for some time, right? And this may also lead to, then again they can start probabilistically at a future point of time. Now this may lead to collisions recurring, right? In certain cases. Also the issue is at what, there is some random exponential back off, so which doesn't tell me that, well, is there a real time guarantee that inside this time a message from here to here we must be going? I don't really have such mathematical guarantee by design, okay. So if there are repeated backups, if I am trying to get on worst case guarantee, which is often required in a real time system, that worst case guarantee will be pretty bad, right? So repeated backups are not a good thing. Also there is no access priority, so there is no well defined rule like and that was very much the reason why this problem happened, because there is no well defined rule which says that when two parties are trying to transmit, who exactly can, because in this case both of them can. So in arbitration, nodes can transmit when the bus is idle, and the problem, like we said, that that happens when these multiple nodes transmit simultaneously, and what we really want is that, well, there should be a priority based arbitration happening, and the node with the highest priority should win, right? So in case of CAN, what we can do is something like this carrier sense multiple access with bitwise arbitration, and this is the thing that we actually do here. So message priority will be determined by the numerical value of this identifier. If you remember, we talked about this 8-bit identifier, right, in the arbitration field, and we will assign that, well, the lowest numerical value will have the highest priority, and this would make things non-destructive, and the arbitration process will be also very elegant. So let's understand what is non-destructive. It means that, well, eventually only one node would be sending the message. So first, multiple nodes will try to send the initial identifier bits, and at that point of time one of the nodes will win the arbitration, and that guy will continue to send its actual message, and the other node will not see its message being sent and destroyed or corrupted by some other node. That thing will not happen. So this is a well-defined rule-based non-destructive scheme, and the arbitration decision is taken by looking at these identifier bits one after another in a serial manner. Okay, so that's why it's called a bitwise arbitration. So what is essentially done is something like you are looking at each of the bits one after another pairwise and doing something like a logical AND. The CAN bus, the way it is designed, the way we have conceived the dominant and the recessive bits. If you remember, we took the dominant as to be a 0, a logical 0, and logical 0 is represented by a voltage difference, whereas logical 1 is represented by absence of any voltage difference between the twisted pairs, and that was a 0, right? So let's see that how this implements this kind of a logical AND. So let's say node 1 and node 2 both are in a dominant state. So that would mean the bus would also remain in a dominant state because there is a voltage difference. Now node 1 is being recessive state, but node 2 is creating a voltage difference, so that's what will be dominating the bus. Okay, so there would be the result would be that the bus would be in a dominant state, right? Now if again similarly for node 1 being recessive and node 2 being dominant, again the bus would be dominant, and if the node 1's output is recessive, that means it's sending a logical 1, which means zero voltage in bus, but node 2 is giving a logical 0, right? So that's already covered, sorry, but let's say both of them are recessive, that means both are giving a logical 1, then the output is logical 1, right? So as we can see that since we are interpreting this dominant as a logical 0 and that is the voltage difference situation, so essentially it's like a AND that is happening. The operation we are doing is AND with dominant being logical 0, right? And the result is 1 only when both of the nodes are giving a logical 1, right? So how does this really work? So first of all, you see, I hope we have been clear that how the way the scheme is designed, how the way we have set the dominant and the recessive bits, it is logically implementing kind of an AND connection without really having any digital infrastructure or anything, right? So that's a nice thing about CAN. And how it works is the two nodes transmit the start of frame bit. Now both the start of frame bits are the same, right? I mean both are having the same polarity, so there is no collision. Now both nodes will start transmitting their message identifiers, right? Now whenever one node gives a dominant bit, what will happen is every node will read a dominant bit regardless of the value written by the other node, because of this property. One is sending dominant, and it's like a logical 0, and like an AND gate is operating by the physics of the system, there will be an output voltage on the bus. So every node will see that output voltage, and that means every node will see that bus being in a dominant state, and it is independent of whether if there is any other node which is sending a recessive bit. Okay, so every transmitting node will always read back, they can read back the bus value which is being transmitted. This is the property of CAN. That means what I transmit, I can see what is happening in the bus, right? So whenever one node finds that I am sending a recessive value, but it is becoming dominant on the node on the bus, that means there is another high priority signal which is there in the bus, and it will just abort its transmission. So as soon as the identifier differs at some bit position, that respective node will just back off. Okay. So here is an example picture here. So let's say you have multiple nodes, node 1, node 2, node 3. So node 3 has the highest priority and node 1 has the lowest priority. How do we know? So all of them are transmitting zeros here, so that's fine. We progress to the next bit. This guy transmits a 1, they are transmitting 0. So node 1 has the lowest priority, that means its identifier value is high, and node 3 has the highest priority, that means its identifier value is the least, right? So here we get a 1, and this is losing the arbitration, and this guy will back off. So these two will remain, and now let's say this guy sends a 1 and this is in 0. So again he will lose the arbitration and node 2 will back off, right? So after this the others will not send any future message, and whatever message node 3 will send, the highest priority node will send, that will continue. And that's how the arbitration system will work in CAN. So what are the consequences here? So nobody but the loser can see that there was a bus conflict, right? Because you see, if you are the higher priority node, you don't even know that there was somebody against whom you won the arbitration, right? Because whatever you are sending, you can see that is going. Only the guy you lost, he saw that, well, you was trying to set something as recessive, but it became dominant, right? So you don't even see, but the loser sees that, well, there is a difference in the polarity, so accordingly the loser will abort respecting the protocol. Okay, the lowest identifier, that is the highest priority, will always win the race. So message identifiers in this way, they are also functioning as priorities, and this is non-destructive because there is no eventual collision that is happening, and this is like a very cool feature here, right? Because it costs you nothing. The voltage signals have been set in a clever manner so that it is coming, this kind of arbitration is just coming for free. That is a good thing. Now this helps you to have a protocol with very high utilization, because you don't have collisions, right? So you don't have collision related transmissions, etc. Until and unless there is an bus error, packets will be transmitted. Only in case of errors in the transmission due to some other physical issue, there can be the requirement of retransmissions. So that's why in CAN you can have a pretty much high utilization, which is not so in other cases of, let's say, CS/CD based things like maximum in Ethernet, where it will be maximum like 37% or something like that. So with this we will stop the lecture here, and we will start from this point again in the next lecture. Thank you.